And my airway's not getting restricted. All right, so today, 3 objectives. O2 transport, CO2 transport, and then a little bit of acid base, which will supplement what we talked about today. So first we'll tackle O2 and the worst figure in physiology. It's not going to be the worst in life. Well, I'm going to try and make it not the worst. It might still be bad, but it's not going to be the worst here. O2 content of arterial blood. So we're talking about arterial blood. What we want to do is describe how do we carry the oxygen. We know we need to carry oxygen in the blood. Where is it carried? How is it that we're able to put oxygen in blood so that it can be transported to tissues? 2 places that we can put oxygen. One is dissolved in the plasma. As a dissolved gas or oxygen. Think about your fish tank with a bubbler, right? The fish are breathing water, they're pushing water over their gills. We know that there can be oxygen dissolved in fluids, and that at least some animals that have gills can extract it. How much of the oxygen is going to be dissolved in our plasma as a percent of the whole? A lot or a little? It's crap. It's like 1%. Terrible. Oxygen is not very soluble in water. It has a very low solubility, which means you can't put much oxygen in water, and especially as you warm water up, it's even less soluble. So for those of you who, I don't know, ever had a tropical fish tank, and the power went out, and you weren't there, and the bubbler stopped working, and then you came back, like after the weekend, and all your tropical fish were belly up, dead, and rotten, because even though the tank is open to the atmosphere, it's so insoluble that the oxygen wasn't able to go into the water fast enough to keep the levels of oxygen high enough in the tank without that bubbler forcing it in. So it's terrible. Our plasma does carry some, but very, very little. What does that leave in the blood that's responsible for carrying oxygen? Red blood cells, and I wrote it twice. Hemoglobin. Hemoglobin is responsible for carrying almost all of it. So about 99%. Of O2. And actually that's the way you could view hemoglobin as a molecule. It's a special color molecule that we continuously make in very, very high quantities, putting inside red blood cells so that our blood can actually carry enough oxygen. What happens if you take the red blood cells out of your blood? Can you carry enough oxygen to stay alive? No. We need it up towards normal hematocrits, and if it starts to dip lower than 40, that's okay, 36, 37, that might be all right, 35, 34, that's anemic condition. You're not going to be able to carry enough oxygen to sustain normal activities. You won't instantly die, but you won't be able to run around the block, for example. So what is hemoglobin? What's it look like? There's a picture right up there. It's a complex molecule. It actually has 4 subunits. Each one of these is a protein that has its own 3-dimensional structure. They're combined together, and then the important part is in the middle, we have an iron molecule. And I don't know if you guys noticed, but that if you have iron and you get it wet and it's in the atmosphere, that it rusts, it oxidizes. So iron has a strong affinity for oxygen. Those iron molecules combine 1 molecular oxygen, that is 1 O2. And since we've got 4 subunits, that allows us to put 1, 2, 3, 4 oxygen molecules in each total hemoglobin molecule. 4 O2s per hemoglobin. Oh, you don't have to memorize this number. I don't even know why I do this. I just sort of like big numbers. Let's see. I should draw a red blood cell and put an arrow. All of the hemoglobin is in red blood cells. Hemoglobin. All of it. There really isn't any that's circulating. It actually has toxic effects on kidney cells. So if it does escape from red blood cells, for example, you run the risk of damaging your kidney. So it should be housed within red blood cells at all times, and there's a lot of them in there. So approximately 280 million hemoglobin molecules per red blood cell. 4 oxygens per hemoglobin equals 1, 1, 2, 0 oxygen per red blood cell. In other words, if we looked at a normal red blood cell, it carries about a little over a trillion molecules of O2 per red blood cell, which I guess is pretty impressive. That's a lot of oxygen in a red blood cell. And we have lots of red blood cells. How good is hemoglobin at binding oxygen? Pretty good. It's very, very well adapted for attracting and holding oxygen molecules. So we could say that it binds O2 well. I'm going to say really well. That's only half the story. Finding oxygen is great, right? You need to be able to pick up oxygen in the lungs. If you're a red blood cell passing through a pulmonary capillary, you want oxygen to bind to your hemoglobin molecules, but then you have to take that red blood cell and bring it to the tissues, and what needs to happen with oxygen at the tissues? You have to release it, right? Like, it's great to pick it up and bind it, but if you don't release the oxygen, it's completely worthless as a transport molecule. So we want to be able to bind it, but also, we could say hemoglobin needs to release oxygen. And there are examples of molecules that hemoglobin is really good at binding, and it simply does not release them. For example, someone said, does that stand for carbon monoxide, not cardiac output? It does stand for carbon monoxide right now. So carbon monoxide. Where do you get carbon monoxide from? Where does carbon monoxide come from? Cars. Anytime you burn anything. So a leaf, fossil fuels, doesn't matter. If it's a carbon-based molecule and you burn it, you're going to make carbon monoxide. Carbon monoxide binds very, very tightly to oxygen. In other words, the carbon monoxide molecule will come in and then bind to a spot that should be holding oxygen, and it binds about 200 times more tightly. Is it going to come off?
No.
Not very easily. Eventually it will, but it tends to stay put much, much more readily than oxygen will. Can we see why carbon monoxide will kill you? Yeah. It itself is not poisonous. It simply takes up a spot on a molecule that should be a spot for oxygen and takes up that space. Have you guys heard of the color symptoms of someone who has carbon monoxide poisoning? The hemoglobin turns like a bright, bright red. Similar color when it binds oxygen, turning that bright, bright red. So people who have carbon monoxide poisoning might have like flushed lips, sort of like say cherry red lips, so like really, really bright. Their hemoglobin has cut a lot of this stuff down to it. How do you help someone who is suffering from carbon monoxide poisoning? Get them in fresh air. This will come off, so if they're breathing fresh air, that's fine. You might give them oxygen if you happen to have it, but the whole deal is you have to get that carbon monoxide off. So I like to talk about carbon monoxide for two reasons. One, so you guys don't barbecue in your house. Ever. There's every single year people barbecue in the house and then they die because there's not enough ventilation and the carbon monoxide builds up. It also doesn't have any odor. You cannot smell it at all, so you don't have any idea. People end up just feeling a little sleepy. They might get a headache. Don't barbecue in the house. And it does a really good job of showing the importance. Binding is great. We need to bind, but we need to release at the same time. So we have words to describe this binding and unbinding. You'll see this term in your books, deoxyhemoglobin. Deoxyhemoglobin is simply hemoglobin that doesn't have an oxygen bound to it, and if we bind oxygen molecules, it will turn into oxyhemoglobin. So they're just words to express, is it carrying oxygen at the moment, or has it released its oxygen? A more useful term, which we're going to use, is percent saturation. As a concept, this makes a lot of sense too. Percent saturation. If you imagine every single one of your hemoglobin molecules in your blood had as much oxygen as it could possibly carry, form oxygen molecules per hemoglobin, you could say it's saturated with oxygen. It can't carry any more, so it would be 100% saturated. If you imagine that you were able to strip off every single oxygen molecule from your hemoglobin, it would be completely unsaturated. I don't like that word. But yes, unsaturated. It would have a 0%. So this is actually a really useful term, and it's going to vary in our bodies from somewhere close, never really quite gets to 100, and it really never gets lower than about 25% saturation. And you might think, well, that's a rip-off. 25% saturation means that it still has a quarter of the oxygen on it. It turns out that the last oxygen molecule out of the four gets bound really, really tightly, and it really just never comes off. So that most of the time, this is the range that we work in, somewhere between 25 and 100% saturation. I did just create a giant mess. 100% saturated means as many oxygens as it could possibly bind. Totally saturated. Does hemoglobin concentration vary? In other words, can you have a red blood cell that has more hemoglobin in it and a red blood cell that has less hemoglobin in it? Sure, absolutely. So we know that red blood cells are produced, they only last about 4 months or so, 3 to 4 months, and in that process of producing them, they have to make all that hemoglobin. They may not make enough. What's one thing that might cause a red blood cell to have less hemoglobin?
They have more carbon dioxide?
No. Think about development. As you're making it, you're busily making it. It's taken months to make these things, making it. You finally made it. It doesn't have enough hemoglobin in it. What could cause that? Yeah, iron deficiency. So, for example, I'll put low dietary iron. How it works. So, from chemistry, Fe means iron. For example, is one way to produce red blood cells that don't have enough hemoglobin. Each subunit needs its own iron. If you don't have enough iron, you're not going to make enough functional hemoglobin. If each red blood cell has less hemoglobin than it should, does it make sense that you might have a normal hematocrit, the normal volume of red blood cells, but that you still can't carry enough oxygen because there's too little hemoglobin? Yeah. So even though we use hematocrit, and hopefully you have a nice definition of hematocrit, something like the volume of red blood cells as a percent of the volume of whole blood. It could be normal, we'll say it's 45%, but it's still possible to be anemic. That is, it's still possible to have red blood cells that don't have enough hemoglobin in them, and so overall you have not enough hemoglobin circulating. I guess what I'm trying to say is hematocrit's not the whole story. Easy to measure, it's a great quick value, but it's still possible to have a normal hematocrit and symptoms of anemia because you don't have enough hemoglobin in each red blood cell. Loading and unloading reactions. These are good phrases, loading and unloading. And you could sort of, stupidly imagine a truck pulling up and loading a bunch of oxygen on it. That's a red blood cell loading. And then out of tissues, pulls up and then dumps off a bunch of oxygen. So just think about loading, putting oxygen in a red blood cell or on hemoglobin, and unloading, releasing oxygen from hemoglobin. What we're really talking about is this reaction. If we load oxygen, we're going to take deoxyhemoglobin, turn it into oxyhemoglobin. If we unload O2, we'll be taking oxyhemoglobin, releasing the oxygen, and turning it back into deoxyhemoglobin. What we want to do is describe where this is going to be happening. So, in the lungs, are we going to have loading or unloading of oxygen?
Loading.
I know this is kind of silly, but I'm going to do it anyway. Loading. O2. And in the tissues? Unloading. So the question we want to answer now is, great, this is totally true. We know that the blood is going to be loading up oxygen in the lungs and unloading oxygen in the tissues. We want to be able to describe how much oxygen is going to be loaded, how much oxygen is going to be unloaded, and the significance of that. How is it that you can unload oxygen? How is it that you can load oxygen? In other words, what's causing this loading and what's causing the unloading? So when we talked about our partial pressure gradients, that was a good chunk of the story. The partial pressure gradients were really useful in determining which direction. When we draw a pulmonary capillary, we draw an alveolus, put a PO2 of about 105, PO2 of about 40 or 45? 40. This told us which direction oxygen was going to be driven, and that was really nice because then we could predict, great, as long as we keep ventilating, keep the partial pressure of oxygen in our alveoli much higher than the blood, we're going to keep driving it into the blood. What we want to talk about now is this oxygen that's coming in, what governs its binding to hemoglobin. That is, it's great to get into the blood, but it's the hemoglobin that does all the carrying, so we want to get the oxygen onto the hemoglobin. And then in the tissues, we want to get the oxygen off the hemoglobin. Let's do tissues. What was the PO2 of blood that's exiting a pulmonary capillary? in the lung alveoli, it was 105 millimeters of mercury. It was about 100. Review. And then coming out of the tissues, the PO2 is about 40 millimeters of mercury. And it makes sense that it would be 40 coming out of the tissues because that's the same blood that's going to the right side of the heart, into the pulmonary trunk, and then back to the lungs. So that number and this number should be out the same. I'm going to make a tissue cell out here. I'll make 2 tissue cells out. So, good. Now we can talk about our loading and unloading reactions. I'll go into a little more detail, but I like to start off with some basic principles. Basic principles. The most important factor that determines how much oxygen is actually going to be loaded onto the hemoglobin inside red blood cells is the PO2. You can say that, the amount of O2. And this should sort of make intuitive sense. If you send a red blood cell through an area of the body that has a lot of oxygen, does it kind of make sense that a lot of that oxygen is going to end up combining with the hemoglobin? It's like tons of it. Oxygen is going to be bumping into things. Oh, it's bumping into the active sites and connecting to the hemoglobin and being held there. Should make sense. So this is the most important factor. And then likewise, you can think about this blood as it runs through a systemic capillary to the tissues, and there's less oxygen present. And there's less oxygen present when those molecules get released. They're much less likely to end up, they're much more likely to diffuse away from the red blood cell and hemoglobin and end up in the tissues where they're going to be used by cells. So that's the most important factor. And then the second is a set of factors, which is complicated, but we'll get to it.
Are you saying that, like, if there's more, if the pressure for the oxygen is up, then there's more oxygen finding?
Correct. Yep. Yep. And we'll show you a nice graph of it. So the second set is really a set of factors. That is, hemoglobin actually affinity 4 actually has a changeable affinity. That is, the attraction, the ability for a hemoglobin molecule to bind oxygen is alterable. Sometimes it binds it more tightly, sometimes it binds it less tightly, and it's based on a couple of things. One is chemicals in the environment of the red blood cell and temperature. Yeah, liking, the amount of attraction, that'll work, affinity or attraction. And the two things we're going to talk about that alter the affinity are specific chemicals, which we'll talk about, and then temperature. And it changes how tightly or loosely oxygen can be bound to hemoglobin. Let us tackle the worst figure in physiology. Oxygen hemoglobin dissociation curve. Sometimes it's called the oxyhemoglobin dissociation curve. It's the same thing. It's a y-axis and an x-axis. On the y-axis, we're going to plot percent saturation. In other words, for a given volume of blood, what percent of the hemoglobin molecules have oxygen bound to them? And this is going to vary between 100%. Every single hemoglobin molecule is going to have oxygen bound to it. And I'm going to put the theoretical 0 down here because theoretically you could strip away every oxygen molecule from the hemoglobin. It's never really going to happen, but at least it's theoretical. And then I'm just going to fill in middle values. 1, we'll have 50%, 75%, and 25%. Make sure everyone's got it before I blaze ahead. Look good? All right, x-axis. is the PO2 of the blood. In other words, the partial pressure of the blood. And this is going to be hard for me to fill in values. We need to start at 0 and go up to 100, and we need mix every 20 millimeters of mercury, which is hard for me to do. 50, 60, 40, 20. It's impossible for me to do. 20, 40, 60. Is it fairly? It's fairly. All right. We set up the axes. All we need to do now is add in 4 points and then play connect the dots. And let's start with something that makes sense. Let's start up the lugs at the lungs, because we already know some values with respect to the lungs. What's the partial pressure of blood leaving the lungs? You could sort of cheat by looking over here if you want to. What is it? 100. All right, so here's the partial pressure, 100. What do you imagine the saturation of that blood is? Completely saturated with oxygen, or at least almost? Yeah, it makes sense. If you send it through the lungs, you better be picking up a lot of oxygen. Turns out it's not quite 100%, but it's really close. I can get this number in. Lungs. So PO2, 100 millimeters of mercury, and the percent saturation, we'll say 98+%. It's almost 100% saturated. It never quite gets to 100%, but it gets really close. Good. Let's do the tissues. Normal blood then flowing to tissues, and the tissues are going to be able to extract oxygen from the blood, and the PO2 in that environment that the tissues are in, because they're using oxygen, is going to fall. What's the partial pressure of blood in the tissues? Normal tissues like skin or the stomach or something like that. Yeah, it's 40. So we look here, normal tissues, PO2, it's 40 coming out of the skin. It's going to be 40 millimeters of mercury in the interstitium of something like the skin. So there's our PO2. 40. For the interstitium in body tissues. Now the question is, where are we going to put the dot? What percent saturation is blood as it passes through tissues? Is it going to be 100%? No, we know it's not going to be 100%. So we know it's going to be less than 100% at least. The only question is, how far down does it go? And it's kind of like asking the question, how much oxygen does tissue extract from blood? 100%? Does it extract all of it? No. 50%? 2/3. 2/3? Half? 2/3 is really close. It's about 70. Excuse me. It's not really close. The inverse is really close. It's about 75%. In other words, most tissues are only extracting about 20%, 25% of the oxygen that's in them. So here's our second value. This is in the tissues. And these are going to be, I'll put non-metabolically active tissues. Active. Or if you want, you could put normal tissues. Just normal tissues. They're not doing anything exciting. PO2 is about 40%. Saturation is about 75%. We're halfway there. We've only got 2 more values to do. I got blue. Now let's think about really metabolically active tissues. The heart, skeletal muscle when it's contracting, those tissues use a lot of oxygen. What's the PO2 in those tissues going to be like? It's got to be lower than 40. Turns out it's about 20. That's about as low as it ever goes. And then how about the percent saturation? We know it's got to be less than 75. It's about 25%. So I'll put a dot there. And that is 3 dots. So we'll call it metabolically. About 20% saturation, about 25. And let's put examples in here. Heart myocardium is a great one. Exercising skeletal muscles. We've got one more value to put in. If the PO2 is 0, that is, there is no oxygen, what's the percent saturation going to be? 0. All right, so we can put that in. Excellent. Now all we got to do is connect the dots. The relationship between these is a sigmoidal or S-shaped curve. So it starts off very, very flat, and then it picks up speed if you want. The slope of the line gets much, much steeper until it hits that. And in reality, this part of the curve doesn't really matter because we can never pull off that last oxygen anyway. So why do we do this, and what's the point of it? A couple of things that are significant about this. Just dropping everything today is going on the floor. Let's tackle this good top bit of the graph. Significance. Look at the PO2s between about 180 millimeters of mercury, and look what happens to the percent saturation. So here's our between 180. At 100, percent saturation is almost 100%. At 80, the percent saturation is, I don't know what it is from this, I didn't have it marked down. It's like 90-something% saturated. What conditions in your life might you experience PO2s that drop from 100 down towards 80? And we could do it like this weekend if we had time. Well, like going up a mountain, like Tahoe. So as you increase in elevation, the partial pressure of oxygen starts to drop. And as it drops, that has the ability to affect the percent saturation. However, since this area of the curve is really flat, and this actually is Tahoe, right, at 84, and I think it's, I can't remember if it's 93%. I'm going to put mine 93%. That might be wrong. I might be off by a couple percent. Going up to Tahoe, 8,000 feet or so, you can still saturate your hemoglobin to 93%. How big of a difference is that compared to sea level? Like 4 or 5% at that. So you can still ski, you can still go hiking, you can still like do all sorts of things that you normally would like to do on top of a mountain. What if this was not sigmoidal? What if this was a flat line? What would your percent saturation be at Tahoe? It would be about 75%. In other words, you would only be able to load up 75% instead of 93%. That's a big difference. Tahoe is actually not that high in altitude. If you crank this up to 10,000 feet or 12,000 feet, then you really start to matter. Get to 60, then you're only able to load 50% if we had a flat line. But since we don't have a flat line, we have a sigmoidal line, this allows you to climb in elevation, lower your PO2, and then still saturate your blood to pretty significant levels.
So does that mean since we have that line, it's really easier to go to gas? Like,
the way to think about it is because we have this line, it allows you to go up mountains at all.
oh,
Like, at all. And Tahoe is no problem. People go up to Tahoe, they don't really notice the difference. You might if you were jogging or being forced to jog. But if you're just like hanging out or hiking or skiing, you might not even notice the difference because you're only losing a couple percent saturation. You can still get almost all the oxygen into your blood that you can at sea level, minus a few percent, which matters at the extremes, but not under most circumstances. And you can keep doing that as you climb in elevation, at least to a point. What else might decrease the PO2 inside your lung alveoli to levels below 100? How about COPD? Asthma? Something like that? Yeah, so if you have a pulmonary disease that's impeding your ventilation, your ability to get oxygen into your lungs and maintain the partial pressure, you can stand to have your partial pressures go down a little bit, have your pulmonary function, have your ventilation reduced a little bit, but as long as you can kind of keep it here, and look at that, and that's a pretty big drop, you can still saturate your hemoglobin to like 90-something%, which will keep you functional. It will keep you alive. So that's one huge significance of this curve, is that up at the top where it's nice and flat, this gives us a lot of flexibility with what's happening in our alveoli. As long as we can keep it above 80 or so, then we don't even really notice if we're at high elevation, or we have a little bit of asthma, for example, at least with respect to oxygen. All right. Second significance. Look what happens to the PO2 between about 40 and 20 mercury. So normal body tissues have a PO2 of about 40, and they're extracting about 25% of the oxygen from the blood. between 40 and 20, again, that's only a 20 millimeter drop, the same amount that we saw here. Look what happens to the amount of oxygen in blood. It's going from 75% all the way down to 25%. In other words, we've unloaded half of the oxygen. So this 20 millimeter difference here is worth less than 10%. Here it's worth 50%. This is basically is an adaptation to increase oxygen unloading in tissues that need it. If the tissues are using the oxygen, what's going to happen to their PO2? They're using it up. It should be going down. Something like cardiac muscle uses a lot of oxygen. It maintains a PO2 at a really low level. When the hemoglobin lands in a capillary running through myocardial tissue, it unloads lots and lots of oxygen, about 50%. That's significant. In other words, we could say something like unloading is enhanced in tissues that need oxygen, which is logical. Tissues that need oxygen, you better unload oxygen for them, or they're not going to be able to sustain their metabolism aerobically. Let's pause for questions on the most difficult figure in physiology, besides the waiters.
So, as long as, like, it doesn't, the pressure, like the 80 over 100, 80 to 100, as long as it doesn't go below 80, then you're okay.
Yeah, as long as you can remain above here, we don't actually have huge changes in saturation. And you can even dip a little by here. I picked 20 to 80, I picked 80 to 100 arbitrarily because I wanted 20, which is what that is. So it's not 80, that's not, I just made that number up. But it's about 80. A little bit less would be fine too. I want exactly 20 millimeters of mercury to match what's really interesting here for our unloading from 40 to 20. You guys all right with this one? Does it seem weird? Make sense? This part should make sense, all right? Makes sense to be able to create a molecule that has a strong enough affinity so that when you go up in altitude, PO2 is lower, that you can still load it up with oxygen. This should make sense too. If it goes through a tissue that's using a lot of oxygen, you want to have it adapted so it's able to sense, whoa, there's very little oxygen here. You know, let's dump it off. Let's unload it so that it can be used by the tissue. All right. The next section talks about how this relationship is modified. And so when you read your book, you're going to see terms like right shifted, left shifted, where you can take this whole entire S-shaped curve and then adjust its position. And I don't do that. I find that all that does is confuse everybody. But we can talk about it qualitatively, how to change this relationship. But we're going to do it in a way that I hope will make sense, and you'll be able to actually make predictions for me, so that I don't actually just have to tell you what's happening. So we're talking about changing the affinity, changing the attractiveness, or if you want, changing how tightly hemoglobin binds oxygen. And it should sort of make sense. If you're going to change these affinities, there's really only two possibilities. Either hemoglobin can bind more tightly, or if we change the affinity, it can bind less tightly. If hemoglobin is binding oxygen more tightly, is that going to favor loading or unloading? It's going to favor loading. If hemoglobin bounds less tightly, it should favor unloading. Good. All right, effective pH. Let's do this logically. Where is pH going to change in the body, like at a local level? Where are we going to see changes in pH? Sure, in the stomach. Thinking not in a lumen, though. About let me ask another way. What gas can change the pH of a solution? Carbon dioxide. So cells are busily producing CO2, and that CO2 goes into their local environment, and it actually goes into the blood as well. What do we know happens to that CO2? It's going to combine with water. So 2 plus H2O, which dissociates into H2CO3, and then plus HCO3 bicarbonate. So we know that the effect of pH, at least if the pH is going down, is because we've created hydrogen ions. And tissues that are metabolically active are using lots of glucose. They're producing lots of CO2. So if they're metabolically active, the pH in that local environment is probably going to go down as they release acids. Wouldn't it be nice if those hydrogen molecules could bind to hemoglobin and tell hemoglobin to release oxygen? In other words, if here's our hemoglobin molecule, and I'm going to put 4 oxygens on it, and if we create a hydrogen ion, if we had a site for it to bind to, so that if it connected to the hemoglobin, that it would change the affinity, make that hemoglobin bind that oxygen a little less tightly, and if it did, that would favor unloading, and then the oxygen would come off. And that's exactly what happens. In tissues that have a decrease in pH, those hydrogen ions bind to hemoglobin and cause its affinity to go down, and then they release oxygen. So there are 4 binding sites. You can do it with all 4 of these things, although one is really not going to do much. Does it make sense? Metabolically active tissues need oxygen. They also produce, ultimately, acids because of the CO2. If you can make that acid give hemoglobin a little nudge to push off the oxygen so that they diffuse out of the red blood cell into the tissues, then you can supply more oxygen to those tissues. So the effect of pH, I don't use this term. It is called the Bohr effect, but I don't talk about it. We can just say that the effect of decreasing pH is to favor unloading, which is logical for a molecule that's supposed to be delivering oxygen to tissues that are metabolically active. I'll erase just the top. All right, effective temperature. If a tissue is metabolically active, what's going to happen to the temperature in that local environment? It's going to increase, right? So the temperature should go up, conducting more chemical reactions. Higher metabolic rate should result in an increase in temperature. What could you, I can't ask the right question. How I can ask it. Is it logical that an increase in temperature causes hemoglobin to lose its affinity for oxygen so that it unloads more? Yep, and it does. So higher temperatures favor unloading. In other words, the affinity that oxygen has for hemoglobin is less as it warms up. So in other words, the warmer you make it, the more oxygen that will be released. And this makes total sense for the heart, which is contracting, or skeletal muscles, which are contracting and generating a lot of heat. Oxygen is released from hemoglobin to a much greater extent in warmer environments. There's one more effect, but I think I'm going to skip it. I'm just going to write it. It's 2,3-DPG, which is a really weird chemical inside red blood cells that change the affinity for oxygen. And essentially that's a chemical that binds to hemoglobin and causes it to release oxygen, so it favors unloading. If you move to high altitude, you'll produce more of this, and it will actually favor unloading in your tissues. But I'm not going to test you on it, so just maybe put a line through it. You can read about it. It would probably be good to read about it, but I'm not going to test you on it. I think just 2 effects is fine. Effect of acid, lower pH, and the effect of temperature. Nice, straightforward, and also easy to predict versus that one, which is not easy to predict, nor does it make a lot of sense intuitively, although it does help. All right, questions on oxygen carrying in blood. Oxyhemoglobin dissociation curve, saturations.
I just wanted to know if the temperature decreases with favor unloading.
Temperature decreases, you're kind of in trouble. Yeah, so we don't have to worry about that. I suppose it probably would, but I don't actually know. Next time we talk about it, and you're like going hypothermic. It might. I just don't know. I don't know. I can't answer that. It'd be easy to measure in a laboratory just with like loose blood in a dish. It's a good thought. Are you guys done with this? Was it as bad as you imagined, or?
Yeah.
It's kind of bad, but it's not too bad. Remember, 1, 2, 3 points, 4 points, make it an S shape, flat on top, steep there, and there's that. It also helps us review our partial pressures, 140.
The colors help.
Yeah, good. CO2 transport, more complicated than oxygen transport. Oxygen transport seems kind of complicated, and it is because of the relationship, but at least there's only 2 ways to transport oxygen, and at least only one of those ways matters. It's all about binding to hemoglobin. When it comes to CO2 transport, 3 ways, and each of them make up a significant fraction of how we carry CO2 in the blood. So first, CO2 can be dissolved in plasma. It's a little more soluble than oxygen is. So approximately 10% of the amount, approximately 10% of the CO2 that we carry in our blood is actually just loose in the plasma. CO2. Second, bound to hemoglobin. About 20%. Besides binding sites for oxygen and binding sites for hydrogen, hemoglobin also has binding sites for CO2. In other words, it can also carry CO2, and it's about 20% of the CO2 is carried as CO2 bound to hemoglobin. And then third, and the most important, is as bicarbonate ions. H2O3. I guess it's the difference, about 70%. In other words, about 70% of the CO2 that we carry in our blood is actually not even CO2. It's converted to bicarbonate, carried in the blood as bicarbonate, and then converted back into CO2 and then released into the lungs. So we have to talk about that. Well, how do you convert this molecule of CO2 into bicarb so that you can transport it to the lungs and then convert it back into CO2 so that you can release it? And luckily it uses the same equation that you know well at this point, H2CO3, which dissociates into free hydrogen ions plus HCO3. And there's our bicarbonate ion. There was an enzyme that makes this happen quickly. Yep, carbonic. You can find carbonic hydrates all over the place. Lining endothelial cells, for example, but where we're going to talk about it most is inside the red blood cells. Inside the red blood cells themselves is where we're concerned about what's happening with the carbonic anhydrase. So let's talk about what's happening in the tissues first. So in the tissues, we know we're going to have partial pressure gradient that favors loading PCO2 something like 45, and then the PCO2 in the blood is something like 40 as it's coming in, and that will drive CO2 into the blood, and then as it leaves, we'll have a PCO2 of about 45. So our CO2 is being driven into the blood. What's going to happen to it once it goes into the blood? So I'm going to draw a giant blood vessel. I'll draw a giant red blood cell, you see, and then we'll have our CO2 going in. Some of it just stays in the plasma. Nothing happens to it. So that's being transported as CO2. Most of it enters the red blood cells. Some of it gets bound to hemoglobin. So I'll draw 4 little subunits and put a CO2 on there. 20% or so. The rest of it is going to be converted. So as it enters CO2, is there water inside red blood cells? Sure, there's water inside all our cells. So it combines with water. And we also have this enzyme en masse, lots of carbonic anhydrase to make this happen quickly, and it forms H2CO3, which dissociates into free hydrogen ions plus HCO3 bicarbonate. So we've done the conversion. Now what happens to the bicarbonate? Well, we're going to transport most of it in the blood. There are channels, protein channels, on red blood cells, lots and lots of them that allow bicarbonate to diffuse freely. So I'm going to draw two arrows, an inward and an outward arrow, because it can diffuse. But if we're creating lots of bicarbonate inside the red blood cell, what's the concentration gradient going to do with respect to movement of bicarbonate? Is it going to push it out of the cell, or we're building up more and more and more bicarbonate inside the cell? It's going to push it out. So eventually we're going to create a massive concentration, and then the bicarbonate is going out. So that's why I'm drawing a big fat line for going out, HCO3. And we've done it. We have made bicarbonate, and we put it into the blood. And that's how we're transporting approximately 70% of it. That's good. Your book's going to mention this thing called the chloride shift. I just don't care about the chloride shift, like, at all. Sure, it's important. Yeah, but whatever. Not much is gained for it. I avoid talking about fluoride as much as I can in this class, mostly because it's a negative charged ion that moves to balance. If you look at bicarbonate, it has a negative charge. Chloride has a negative charge. It's simply going to move to balance. Big deal. We don't have time for the lungs, do we? 2 minutes. We don't really have time for the lungs, but I have time to set the stage. In the lungs, are we going to be loading oxygen?
Yes.
O2. So as oxygen goes in, right, are there hydrogen ions probably bound to hemoglobin? Sure, and actually that's where some of these things go. They'll actually be bound to hemoglobin. As oxygen binds, those hydrogen ions come off. And if you start releasing hydrogen ions, and we have bicarbonate, hydrogen plus bicarbonate can form together, and that's going to start next time. So we'll start that. And it simply reverses the process.